Welcome to The Explainer. Today, we're taking a seriously fascinating journey from the completely invisible, microscopic science of metals all the way up to the massive, real-world steel plants that literally shape the built world around us. I mean, have you ever looked at a towering skyscraper or maybe a massive industrial machine and wondered how the raw materials actually hold up under all that intense pressure? Well, today, we're going to unlock that mystery. We're exploring how tiny, microscopic changes inside a piece of steel translate into giant leaps in performance. And then we'll look at the incredible macro engineering it takes to produce these materials on a global scale. Okay, to kick things off, let's think about a specific engineering mystery. Picture a simple steel shaft sitting inside a piece of heavy machinery. During operation, it's subjected to an immense load. Let's say 400 megapascals of stress. Now that is a staggering amount of force. But here's the thing, the shaft doesn't break, it doesn't even bend. It just keeps spinning, taking that load day in and day out. So why? What exactly is happening inside that metal that lets it behave this way under such immense stress? Where does that load-taking capability actually come from? Okay, let's dive right into this and map out our micro to macro journey. First up, we'll uncover the secret strength of metals. Second, we'll look at chemical versus physical metallurgy. Third, the material science tetrahedron. And finally, number 4, real-world steel engineering. Section 1. The secret strength of metals. So, where does that incredible load-taking capability actually come from? Well, the short answer is found right here in this definition. Properties. A material's performance comes directly from its unique properties. Think about it. If you took that exact same mechanical shaft, taking a 400 MPa load, and made it out of copper, or maybe cast iron instead of steel, it would absolutely fail. Why? Simply because copper alloys and cast iron have entirely different properties than steel. And where do these basic properties come from? They originate from the material's chemical composition. A low-carbon steel is going to behave differently than a high-carbon steel or a titanium alloy simply because its chemical makeup is different. But, as you'll see in a minute, chemical composition is really just the beginning of the story. Moving on to Section 2. Chemical versus physical metallurgy. Now, before we get too deep into how we manipulate those properties, we need to make sure we're focusing on the right kind of science. You see, in the world of metals, there are two really distinct phases. First, you have chemical metallurgy. This is the raw extraction phase. All metals exist out there, and the earth has oxides, right? Iron oxide, aluminum oxide, copper oxide. Chemical metallurgy is basically the process of taking that ore out of the earth, tossing it in a blast furnace, smelting it down, and converting it into a pure metal or a basic alloy. It's all about getting the usable material out of the ground. But for everyday engineering and day-to-day applications, our focus shifts entirely over to physical metallurgy. Physical metallurgy isn't about extraction at all. It's the science of understanding and altering a metal's physical behavior and its properties. It's essentially asking the question, okay, now that I have this steel, how do I change its structure to increase its strength for my specific application? All right, Section 3, the material science tetrahedron. Now, this tetrahedron right here, it's the central, recurring framework that dictates absolutely everything about how metals perform out in the field. It links 4 critical elements: composition, microstructure, processing, and performance. And it's a brilliant linear relationship. We already established that your starting properties come from your composition, right? The chemicals in the metal. But composition alone isn't enough to get maximum performance. To get there, you need to alter the metal's internal microstructure. And how exactly do you alter a microstructure? Through processing. Things like forging, cold drawing, or heat treating. If you want the right performance, you absolutely must have the right properties. To get those properties, you need the right composition paired with the exact right processing to achieve that perfect microstructure. It's like a giant puzzle where all the pieces are permanently linked together. Now, what's really interesting about this slide is just how dramatic this processing effect can actually be. Let's go back to our steel shaft example. Say you produce a steel shaft through a basic casting route, and it comes out with a load-taking strength of 300 megapascals. Not bad, right? But then you take that exact same shaft and put it through a specific hardening and tempering heat treatment process. Suddenly, its strength doubles to a staggering 600 megapascals. No way, right? But it's true. Just think about how wild that is for a second. During that heat treatment, you didn't add a single new chemical. You didn't alter the composition at all. Actually, scratch that. You didn't even melt the metal. The secret sauce of this massive strength increase is entirely internal. The heat processing invisibly rearranged the metal's microstructure. That restructuring is the exact thing that gives the metal its newfound doubled strength. That is physical metallurgy in action. and it's practically magic. Let's move to Section 4 and see how this builds into real-world steel engineering. Understanding the material science tetrahedron in theory is one thing, but executing it on a global, industrial scale, that requires some unbelievable macro engineering. And this is exactly where organizations like MetaTechX engineers come into the picture. They're a leading engineering services provider operating in the global south, and they really represent the real-world embodiment of the science we just learned. They use the latest technological advancements to manage the entire life cycle of steel production. When we talk about controlling composition and microstructure out in the real world, MetaTechX are the people designing and managing the massive industrial facilities required to actually pull it off. Just look at the sheer scale of the facilities they engineer. They manage steel melt shops, or SMS, where that crucial chemical composition is dialed in perfectly. They engineer hot rolling mills and ERW tube mills, where the really intense processing and structural shaping happen. And their services cover the whole shebang, everything from designing brand new projects from scratch to modifying existing plants, providing consultancies, and even managing annual maintenance contracts, or AMCs. They're out there ensuring that at every single step, this incredibly complex science of steel processing is running flawlessly at a massive scale. But hey, macro engineering isn't just about giant machines, right? It's driven by brilliant minds. I think it's absolutely crucial to put a human face on this. The expertise needed to execute physical metallurgy at this level requires seriously dedicated specialists. MetaTechX relies on leading experts to make this happen. People like J.K. Swamy, handling project and planning, Deepak Goswami, managing those ultra-complex electrical and automation systems, S.K. Mishra, leading research and development, and Harish Sharma, overseeing operation management. These are the actual, specific professionals turning the theory of the material science tetrahedron into physical reality every single day. And what I find really compelling is that MetaTechX doesn't just build and maintain these mega mills, they're actively empowering the whole industry. They understand that the intricate science of metallurgy needs to be passed down. So they provide employee training, specialized certification programs, and comprehensive online courses for both students and professionals in the steel industry. They even run dedicated technical blogs that cover hot rolling, steel melting, and continuous casting practices. They aren't just processing steel, they are actively educating the next generation of engineers to master the science. So as we wrap up this explainer today, I want to leave you with a thought. We are literally surrounded by steel. We trust our lives to it every day in the cars we drive, the bridges we cross, the buildings we work in. But it's not just metal holding us up. It is a carefully engineered balance of composition, perfectly processed to achieve a very specific, invisible microstructure. So the next time you look at a massive steel structure, will you just see the metal? Or will you look past the surface and appreciate the hidden, microscopic science that was engineered to hold up the world? Thanks for joining me on The Explainer, and keep looking deeper.